So moving along, chapter 2 here, proportional reasoning, section 2.2. Ratio here. A ratio is comparison of two quantities by division. There are three different ways to write a ratio. One is to write as a fraction. For example, there 1/2. You could put 1:2, or you could also do 1:2 using the words 2. Okay, so there are three different ways to write ratios. Now, why do we need to know ratios? Because we use ratios to work with proportions. All right, so proportion sets two ratios equal to each other. Another way to look at it as equivalent fractions, kind of. 2/3 equals 4/5, 4/6. For those people that see it as equivalent fractions, this gets a lot easier for them. A rate is a ratio that you see almost on a daily basis. A ratio that compares two quantities measured in different units. So rate, the key is there, the different units. And again, this is something you see every day probably driving to school. Miles per hour. That is a rate. When you go to fill up your car, how many times do you think about your miles per gallon you're getting in your car? That's a rate. Okay, so you're taking miles over gallons. Another one is the price for gas per gallon. Okay, money per gallon. That's a rate. All those are different rates. Okay, so again, when you see a ratio, it's kind of on a frequent basis, but you see it more on a rate than you do anything else. Similar, we're going to talk about similar figures today. But two figures are similar if they have the same shape, but not necessarily the same size. So, have a small triangle and have a big triangle there, right triangles. They can be similar. Has anybody in here ever made like a model car or a model plane or train? Anything ever done something like that? Those are similar as well. That's kind of why they're a model. They're the exact same replica, just a lot smaller or a lot bigger depending on how you're looking at it. There's those similar figures. And then we're going to focus a lot on the indirect measurement today. This will be the kind of the tail end of everything. But we're going to focus on the similar figures and or proportions to solve indirect measurement. Now this is a process used to solve for something that you can't normally figure out. Okay, so something like if something's really, really tall and you want to find the height of it and you can't get a ruler all the way up there or get a meter stick or something like that, you can use indirect measurement with some different ways in order to solve it. But again, it's based on the whole similar figures and proportions method. Okay, so again, if you can do number 1 on the warm-up here today, you'll be pretty good off. All right, so proportions here. Again, proportions, you typically use cross products to solve the proportions. A lot of times people will say, cross multiplication, same idea, but really you're going to multiply your diagonals, then you set them equal to each other. From there you're solving for a variable, dividing by 5, and you get your answer. The biggest thing I like to tell students is always check, does the answer you're getting make sense? As in, a lot of times with proportions, you always have either the numerator or denominator, one of them is larger than the other one. Always check on what you're solving. If you plug it back in, the same should still be true. Okay, the numerator and denominator should still be larger. And then you can use proportions to solve percent problems. Now they say percent over 100 equals part over whole. Does anybody know another way to say part over whole? What's the other two words a lot of times you hear of? Is over of. Yep. It's the same thing as instead of part over whole, you use is over of typically, and that comes from the words within the expression. But you can use cross products to solve for percents as well. And they see that there. All right, number 1 here. So I have 1/7 equals x over 56. Now, some of us who want to use cross products here, I would take 1 times 56, giving me 56. 7 times x gives me 7x. Divide by 7, and I get x to equal what, Andy? 8. Now, if we go back here and look at this problem, does anybody see equivalent fractions with that? Does anybody say, hey, I see equivalencies? Anybody? Well, I see equivalent fractions because 7 times what is 56? 8. So 1 times 8 is what? 8. I get the same answer. Okay, because they're equivalent, I can see them as equivalent fractions just the same. So when you have problems like that, it's a lot of times it's a lot easier to see equivalent fractions. If you do proportions, though, you still get the same answer. Number 2, using cross products here, what do I want to multiply, Colin?
60 and 20.
Gets me what? equals, what else do I multiply then?
25 times x.
So 25x. And now I divide by 25. So 1200 divided by 25 is going to give me x equals, John? 48. Nice job. And again, if I look to plug that back in, it makes sense. Numerator is larger, numerator is still larger in my second one. Now, number 3 is the one that you'll probably see more of on like a quiz or test. Okay? You can still use cross products to solve this. There's just a key difference. I take 7 times 12, nothing new there. What's 7 times 12, Jack? What's 7 times 10?
70.
7 times 2. 14 plus 70 is? Thank you. So I get 84. Now I need to multiply my other diagonal. And here's the one where people are going to make their mistakes. X plus 3 is kind of like a quantity times 2. So I need to almost distribute that 2 or take 2 times everything, giving me 2x plus 6. Taking that 2 times the x and taking the 2 times the 6. So now I multiply that, and now it's just a two-step equation I solve. So I subtract the 6, giving me 78 equals 2x. Divide by 2, and I get x to equal what, Reagan?
39.
Nice job. X equals 39. Okay, so recognize, if I have a quantity up there, I need to make sure I multiply with both of them. And then the last one here, we have a story problem. The ratio of boys to girls in a soccer league is 4 to 5. If there are 52 boys in the league, how many girls are there? Now, you're going to hear me say this a lot today, but the key to setting up kind of story problems is you have to be consistent. I don't care how you set the proportion up, but you have to be consistent. So, for example, if I go boys to girls as 4 over 5, when I set up my second proportion, I need to do the same. Boys over girls. I have to have that same proportion or that same ratio set up. So I set up 52 over x because I use the quantity of boys to girls. Okay, I have to be consistent in how I set that up. So now I use cross products to solve, and I get an answer of what? Mark, you have it? 65. Nice job. And again, the biggest thing is just being consistent in how you set that up. Try these 3 on your own. All right, number 5. What did you get for answer number 5, Bailey? 15? Nice job. X equals 15. Number 6. What did you have for answer number 6, Sean?
I got a half.
X is not a half. X is actually, John? X is 5. Now, when I set it up here, I did cross products, giving me 14x equals 10x plus 20. Taking that 10x plus 20. Oh, that's probably where you got your half. You didn't take the 10 times the 2, did you? Take the 10 times both of them. Okay, now I subtract 10x, giving me 4x equals 20. Divide by 4, and I get x equals 5. When I plug that in, it gives me 7/14 equals 5/10, which they're both a half. That makes sense now, as I check it out. Then the last one, number 7. Slug travels 4.5 inches in 120 minutes. I have my first ratio, 4.5 over 120, equals, at this rate of speed, how long would it take the slug to travel 12 inches? So 12 inches over x. When I work that out, I get an answer of what, Andy? It's not 80. It's not 80. Garrett?
320.
It is 320. Nice job. You get 320 minutes. Okay, so let's go. Those are kind of like the basic proportion type problems. Now we're going to get into some of the tougher stuff here. So when can we actually use this? Well, we can apply this to when we need to find kind of these indirect measurements and we can't, stretch out and actually find the dimensions. All right. So for example here, proportion can be used to solve problems about indirect measurement. For example, Jake is 6 feet tall and casts a shadow 15 feet long. At the same time, a tree casts a shadow 50 feet long. So what that means here is if I had a sun up here, and it's casting these shadows down, these shadows are the exact same proportion. Okay, they're proportional. The taller you are, the farther shadow you are. The shorter you are, the shorter the shadow is. It's proportional. Okay, so that's where I get these proportions. So I set up my height and shadow, and I get these similar triangles. Now, the key to all this is being consistent. I personally always like to go height over shadow. Why do I do height over shadow? Because if I look here, it kind of makes my ratios for me. 6 over 15, h over 50. Hey, that's what I have right here. It kind of sets up that ratio, those proportions in a sense. Okay, so I'm always going to go height over shadow over the small one, then height over shadow over the bigger one, and I use proportions to solve. Okay, so this is just one way to use indirect measurement. So let's see what this one looks like. Number 8, a tree casts a shadow of 7.5 feet long. Now we talked earlier, does anybody know about Bob Ross? Anybody know who Bob Ross is? Painter. What's his famous line? Anybody? Happy trees. That's all I draw, man. I draw these happy little stick trees. If you've never seen Bob Ross, you need to know who Bob Ross is. This guy's amazing. You've seen Bob Ross? Great guy. So there's my tree. Okay, my tree's casting a shadow of 7.5 feet. A woman standing 5 foot tall. Now, I'm a terrible artist, so I use stick figures. But she's 5 feet tall. She casts a shadow of 3 feet. Now, I want to find the height of the tree. Now, if I look here, I am given these kind of similar triangles. So using what I know, I'm going to set ratios up, set them equal to each other. 5 over 3, height over shadow, equals x over 7.5. And again, height over shadow of the second one. I have to be consistent. I can't go height over shadow on one and shadow over height on the other. That's where you get your mistakes. That's where you get your wrong answers. Be consistent. Height over shadow, height over shadow. Now I have that. Now I use cross products to solve. So 3x equals 5 times 7.5 is, I believe, 37.5. So I get 3x equals 37.5. Divide by 3. And I get x to be my height, which my height is then, I believe, about 12.5. Am I right? Look at that. Without a calculator. Be impressed, Jack. It's all right.
Yeah.
Okay. But again, the key there, being consistent. Height over shadow, height over shadow. I don't care which way you set it up, just be consistent. Diagrams do help. Okay? Try these two. On your own here. Try these two. Draw diagrams if you need to. But try these two the same way. Height over shadow, height over shadow. All right, as you look at this, what do you have for an answer to number 9? Sean, what do you have?
9.75.
Nice job. Yeah, 9.75 feet is correct. Now, as you plug that back in, yeah, that makes sense. It's less than half. The shadow of the height to the boy, it's less than half. So if you plug that in, less than half. That makes sense. And what about number 10? Reagan, what do you have for number 10? 42 feet is correct. Nice job. Again, using that indirect measurement, you can find heights of all these really tall buildings and skyscrapers and such. Last thing here. You can use the same thing in relationships to maps. Okay, so the same idea, you can use it to find distances in maps or distances. But the scale on a road map is 1 inch equals 10 miles. So boom, I have my first ratio, 1 over 10. 1 inch, 10 miles. You want to find out how far Waterloo and Lincoln are. On the map, they are 5 inches. So it's inches with the numerator. I go 5 over x. Now here's one where you might be able to see equivalent fractions, hopefully. How do you get from 1 to 5? Multiply by. So 10 times 5 gets me, I get 50 miles. Again, could I use proportions? Yes, but on a problem like this where you have something with 1, it's a lot easier sometimes to just see the equivalent fractions. Now, same thing on number 12. How about Waterloo and Fremont, who are 2.5 inches apart, or 2.5 inches apart? Well, how far apart are they going to be, Ethan? 25? Nice job. So again, use that same thing, indirect measurement, proportions, subscales. But again, the biggest thing is be consistent. I don't care which way you set it up, just be consistent in how you set it up. And that's it for today. There's your assignment.